Okay, this is the last part, guys. This is divergent theorem. Divergent theorem is super fantastic, connecting one surface integral and one closed surface and one triple integral and the solid formed by this closed surface. In the picture you can see, for example, here in blue color is a surface completely the part out. The solid is like a skin of the solid, and the solid is completely inside. The solid is completely solid. The rock here solid. Okay, this is a state relationship between. This is like a flux. This is a flux. Exactly, but you complete the flux now. We're using the triple integral. Okay, remember diverging. The interpretation of this is a source. Suppose that we have inside here a source. Okay, divergent give me the interpretation for the source. So this is like a flux is equal, you know, the source inside the triple integral. This is hard to understand the interpretation, but it's the idea. Okay, let's see example. Okay, this example is nice. This example is computed the surface integral and the closed surface of this element, and the surface is given, no? The surface is a sphere. Es a sphere que es x squared plus y squared plus c squared equal a squared, and a is the radius for the sphere. Sphere with the center and the origin, 0, 0, 0. So I want to go to the divergent theorem. Divergence say if the surface integral is equal f that ds is equal to the triple integral and the volume C of the divergent of the vector field dv. This is the idea for the divergent theorem. Entonces in this case a little bit confusing, it's not clear who is capital F. I suppose que capital F is the vector x qv, comma y qv, comma c qv, no? It's a PQR, PQR, because the rest is ds. Is a normal vector, right? Okay, in this case is this and this together, no? Is dy dz, comma dx dz, comma dx dy. Okay, entonces let's compute it first. The divergence. Divergence of the vector field f. The formula is partial derivative p with respect to x plus partial derivative q with respect to y plus partial derivative r with respect to c. And it's PQR. Entonces es 3x squared plus 3y squared plus 3c squared. See, for example, I try to compute using the triple integral. Okay, the second part of the divergent theorem. I need to think about what's the best way to set up this triple integral. I suppose que it's a spherical coordinate. It's a spherical coordinate. Entonces, si you factor out 3, for example here, 3, we have x squared plus y squared plus c squared plus rho squared. Okay, entonces in our triple integral, the divergence is 3 rho, and the rest is rho squared sine phi d rho, d phi, d theta. But let's come back to the surface. The surface is the sphere, right? It's a sphere. The sphere, the equation is x squared plus y squared plus c squared equal a squared is the radius of the sphere. But this is outward orientation, outward orientation. Ok, eso dos. Entonces, si yo integré first with respect to the rho, es from 0 to a, que es the radius for the sphere. Si yo integration the complete sphere is from 0 to pi, phi, and from 0 to pi, theta. And we can separate this integral in three integrals. The first integral is 3 is a common factor, rho square and rho square root 4. So actually it's 3 times integral from 0 to a of the rho 4, the rho, time integral from 0 to pi sine phi, d phi, time integral from d theta from 0 to pi. This integral obviously is 2 pi. This integral is rho to the 5th power divided by phi. Entonces, evaluating between 0 and a is 3 times a to the 5th power over phi. Integral de sine es minus cosine, and minus cosine theta, evaluating between 0 and pi is minus cosine phi plus cosine 0. This is negative 1, but another negative become positive. 1 plus 1 is 2. This is 2. But the final answer is multiplication of 2 times 2 is 4 times 3 is 12. 12, a to the 5th power. Phi, don't forget the phi, divided by phi. And this is the final answer.